Welcome to a second example on the applications of extrema of functions of two variables. The goal of this video is to minimize the surface area of a box with a given volume. Let's go and take a look at our problem. Here we have a box without a top that has a volume of 32 cubic feet. We want to find the dimensions that minimize the surface area. Let's call this the length, this the width, and this the height. So one thing we know for sure that the volume is 32 cubic feet. The volume of this box, which is a rectangular prism, would be length times width times height, which must equal 32 cubic feet. Now let's come up with an equation for the surface area. We'll call it big S. Since this box does not have a top, there'll be 5 faces that we need to consider the area for. Let's start by talking about the bottom. The area for the bottom would be L times W, or length times width. Remember, there's no top. Now the right side and the left side would have dimensions h by w, so the surface area of the left and right would be 2 times h times w. Now the area of the front face would be length times height, or L times h. There's also one in the back, so we have 2 times HL. Remember, we're trying to minimize this surface area. Well, right now we have a function s in terms of 3 variables, and our goal is to rewrite this in terms of 2 variables. So what we can do is go back up to the volume equation and solve it for one of the variables. So if we were to solve this equation for L, we would have L is going to be equal to 32 divided by WH. Now wherever we see an L, we can replace it with 32 divided by WH. So we'll perform substitution here and here, and this will give us an equation in terms of 2 variables. So we'll have S is going to be equal to 32 over WH times W plus 2HW plus 2H times 32 divided by WH. Let's go ahead and simplify this. Notice the W's simplify here and the H's simplify here. So we have S is going to be equal to 32h to the negative 1 plus 2HW plus, this would be 64W to the negative 1. So now we have a function S in terms of 2 variables, H and W. So now we're going to follow the rules for determining the relative extrema for a function in 2 variables. Again, we're going to determine the first order partial derivatives and then determine whether they're both equal to 0 or where they don't exist. And then we'll perform the second partials test to see if we actually have a relative min, max, or neither. So let's start by finding our first order partials. So the first order partial with respects to h is going to be negative 32 h to the negative 2, or negative 32 over h squared, plus this would be 2w, and this would be 0. So we need to determine when this equation is equal to 0 and when the partial with respects to w is also equal to 0. So the partial with respects to w would be 2h, and this would be minus 64 w to the negative 2, or minus 64 over w squared. So we need to solve this system of equations. Let's rewrite this on the next slide. So we'll solve this system using substitution. Let's go ahead and take this first equation and solve for w. So we'd have 2w is going to be equal to positive 32 over h squared. And then we'll go ahead and multiply both sides by 1/2. So this tells us that w is going to be equal to 16 divided by h squared. Now we'll replace w in the second equation with 16 divided by h squared, and we'll have one equation in terms of one variable. Let's go ahead and simplify this. This is the same as 64 over 1, and then instead of dividing by this, we'll multiply by the reciprocal. We'd have h to the 4th all over 16 squared. This will give us 2h minus 1/4 h to the 4th equals 0. Now let's factor out the common factor of h. we'd be left with 2 minus 1/4 h cubed equals 0. So now we know h could equal 0. And now let's determine when 2 minus 1/4 h cubed is equal to 0. Let's move the h to the third term to the other side. We'll have 2 equals 1/4 h cubed. Multiply both sides by 4. We'd have 8 equals h cubed. So h is equal to 2. Now remember, h refers to the dimensions of the box. There's no way that h can be 0 because the volume would be 0, so we can exclude that value. So when h is 2, let's go ahead and determine what w would have to be. Remember, w is equal to 16 divided by h squared. Well, 16 divided by 2 squared would be 16 divided by 4, or 4. So we have a height of 2, width of 4. Remember, we also know that the volume is equal to 32 cubic feet. So if the height is 2 and the width is 4, this would be 8. 32 divided by 8 would equal 4, so the length is also equal to 4. And of course, these are all in feet. So we may assume that the surface area will be minimized when the height is 2 feet, the width is 4 feet, and the length is 4 feet. But really, to be sure, we should determine the value of d as we see here and make sure we have the conditions that represent a relative minimum. So let's go ahead and take the time and do that. So let's go ahead and rewrite our first order partial derivatives. So here we have our first order partials from the previous screen, and I went ahead and rewrote them using negative exponents here. Let's go ahead and find our second order partials. So the second order partial of h would be positive 64 h to the negative third power, or 64 over h to the third. And the second order partial with respect to w would be positive 128 w to the negative third, or over w to the third. Then the mixed second order partial would just be 2. And remember, the values we're considering are L equals 4, W equals 4, and H equals 2. So when H is equal to 2, this second order partial would be 8. And when W is 4, this second order partial would be 16 minus 2 squared. Well, of course, that's going to be positive. And the second order partial with respect to H was also positive. So we have met the conditions for a relative minimum. D is positive, and so is the second order partial with respect to, in this case, H. So we do have a relative minimum. So this does verify that these dimensions do minimize our surface area. Let's go ahead and finish by determining what that surface area would be. So here's the formula that we had for the surface area of our box. Let's go ahead and just substitute in the values for L, W, and H. L times W would be 16 plus 2 times H times W would be 8 plus 2 times L times H would be 4 times 2. That's also 8. So we have 16 plus 16 plus 16. Of course, that's 48 square feet for surface area. I hope you found this example helpful.